Okay, we are talking about the efficiency of gas turbine. So this gas turbine efficiency or gas turbine performance, they are actually influenced by several parameters. Okay, we have 5 parameters that we are talking about. Okay, these are the things that we can do maybe to improve the performance or to improve the efficiency of our gas turbine. The first one is the compressor inlet temperature. So you know that fresh air comes into the compressor first. So we are talking about the ambient air, the fresh air that goes into the compressor. So we call that compressor inlet temperature. And then the second one is the compression ratio. Okay, compressor ratio. We know that the higher the compression ratio, the higher the efficiency, but up to the certain limit lah. Okay, and then we have turbine inlet temperature. Now, when we talk about turbine inlet temperature, this is actually the temperature of combustion gas that comes out from the combustor after combustion process. Okay, and then we will look in detail later on how the turbine inlet temperature it affects the gas turbine total performance. Okay, the fourth one is the exhaust temperature. This is the exhaust gas after it leaves the turbine, right? And then the last one is of course the air flow rate. When we talk about the mass flow rate, it also has a significant effect in terms of the performance of our gas turbine. Okay, let's have a look at the first factor that determine or that affects the gas turbine performance, the compressor inlet temperature here. We are talking about the fresh air that comes into the compressor. So usually this one, in general, it is very difficult to control, okay, because you are talking about the ambient. Okay, we know that lower ambient temperature, okay, will result in the lower heat rate and better efficiency because of the higher pressure ratio. So how does it work? Okay, when the ambient temperature is low, basically at lower temperature, we know that the density is higher. Okay, the density high means that you can put in more air, okay, into our compressor. Okay, when more air comes into the compressor, of course you are getting higher efficiency, okay, because you can simply have a higher compression ratio, pressure out from the compressor divided by pressure in. This is given by the efficiency equation, okay, the approximate efficiency equation that describe here. Okay, this number P2 divided by P1 here, if this is high, the whole term on the right hand side here is small, and then so you have 1 minus something that is very very small, so you will get a maximum number of efficiency. So that's how the ambient it affects the gas turbine performance. Okay, when you are looking at the Malaysia point of view, our ambient is around 35 degrees Celsius. So you compare to other cold countries, which ambient is maybe 20 degrees Celsius or 10 degrees Celsius. So their performance for gas turbine is very much higher as compared to the country, okay, which is having a higher ambient temperature. Okay, that's why it is written here. Same gas turbine may perform differently in two different countries because it depends very much on the ambient condition. Okay, the second factor is the compression ratio. Okay, this is fairly straightforward. You can increase the compression ratio to get the increase in the performance. Okay, however, we cannot simply increase the compression ratio, as I mentioned yesterday, up to 50 or up to 100 because there are limits to it. First of all, it is limited by the number of stages. Okay, maybe in our compressor, the approximate number of stages is around 8 to 10, or probably around that numbers. You can make it to 100, but that is not practical because, of course, we need to spend more money in terms of building the material that is used for the compressor. So there are some kind of limitation to that, okay, in terms of how we can increase the compression ratio. In addition to that, okay, we have seen from from our previous slide, let's go through our previous slide here. Okay, the relationship between the efficiency and also compression ratio, which is given by this graph, right? Okay, if you look the relationship here, even though we increase our compression ratio to a high number, let's say from 20 to 25 compression ratio, you can see that there is not much increase in the efficiency. But the effort for us to get the compression ratio high, I mean the work consumed by the compressor is very much higher lah. Means that you are getting very small increase in the efficiency for the high effort that we need to make in order to make our compressor works. So from that point of view, there is no point of us trying to increase our compression ratio as high as possible, because the benefit is not as good or as high as what we expected, compared to amount of effort that we need to put in. Okay, when you talk about the compression ratio here, we might be requiring the intercooler, to reduce the temperature of air after the compression. So I will go into detail, on what the intercooler is later on. And then we have another factor that affects the GT performance, which is the exhaust temperature. Okay, exhaust temperature, we are talking about the temperature or the gas that exit the turbine, the gas turbine. So lower exhaust temperature, of course, it will increase the turbine output. We are talking about the temperature difference. Okay, when we talk about the exhaust that comes out from the turbine, if the temperature is still high, means that the delta T, the temperature difference is small. So whenever you have a change in temperature which is small, usually the efficiency is small as well. So we try to make our exhaust temperature as low as possible in order to increase our efficiency. But again, it is also limited by the geographical location of our gas turbine lah. Means that it is very much dependent on the ambient. So this is kind of difficult to control, but actually there are some methods that we can use to make sure that our ambient is relatively low lah. Right, yeah.
Can you explain more on how the ambient temperature influence the efficiency?
Okay. When you talk about ambient, when I talk about ambient just now, the first one, ambient, it affects the inlet to the compressor, right? You have a fresh air that comes into the compressor. So that is one factor that relates to the ambient condition. The second one is the ambient. We are talking about the exhaust temperature. Okay, let me go back to the compressor inlet temperature. Okay, this is also ambient. When you talk about compressor inlet temperature, this is relative to the air that goes into the compressor. Right. If we compare cold countries, let's say the ambient condition is around 10 degrees Celsius, and then we compare to Malaysia, the ambient is around 30, 35 lah. Let's say 35 degrees Celsius during the hot weather lah. Okay. When you talk about ambient temperature, we are talking about the density of air. Okay, at lower temperature, density is higher. Okay, density of an air, it is a function of temperature. But even though it is not much, but if you are talking about the amount of air that is relative to the density, you can consider high lah. So at higher temperature, density is low. So when you talk about density low and also density high, we are talking about the mass flow rate. Okay, at lower density, the mass flow rate that goes into our turbine is low lah. Okay, at higher density, the mass flow rate that goes into our gas turbine is high. So you are admitting more air into the compressor. It will result in higher compression ratio. So at the end of the day, you are talking about better efficiency lah at higher density. Higher density, it is related to the colder ambient. So that's why it is affecting the compressor inlet temperature. It is affecting our efficiency or GT performance. The other factor is we are talking about ambient just now is actually relative to the exhaust temperature. Exhaust temperature means you know that after combustor, air goes to the gas turbine. After the gas turbine, work has been extracted, and then it will be released to the ambient, or it will release to the chimney lah, to be exact. So that is the kind of temperature that we are talking about after the gas turbine. It is actually the ambient condition lah. Okay, when the temperature of the air that exit the gas turbine is high, you are talking about temperature difference. Temperature difference between TH and TL, which is when TL is high, then the temperature difference delta T is low. Okay, whereby when you have in cold countries, for example, the ambient temperature is low, the change in temperature delta T is high. Okay, so usually when you talk about efficiency, you're talking about the change in temperature. If you look at the equation, one Carnot efficiency for a heat engine, 1 minus TL divided by TH. Okay, when our TL is high, TL divided by TH is actually, TH is the combustion temperature kan. Okay, so 1 minus TL divided by TH2 overall will become higher if our TL is low. And then on the other hand, for hot country, 1 minus TL divided by TH, TL is high and then the overall efficiency is low. So that's why it is related to the overall efficiency, okay, for the gas turbine performance. So typically, the exhaust temperature that goes out from our gas turbine is high, 500 degrees Celsius to 600 degrees Celsius. This is the quite high temperature. This is, if we are applying it to an open system or open cycle, you imagine you are releasing exhaust gas 500 to 600 degrees Celsius. So this is equivalent to very, very high enthalpy. So actually you are wasting the energy. That's why it is best if we can adopt the combined cycle. We can use this temperature or this energy to heat up water, convert it into steam, then you have another power in the steam turbine. So that's why I say here, okay, it is significant for the combined cycle lah, for the heat recovery steam generator in the power plant. So this is how the exhaust temperature or the ambient temperature after the turbine, it affects our gas turbine performance.
Okay, thank you, sir.
Okay. All right. The last factor or the another factor here is turbine inlet temperature. Now you have turbine inlet temperature. This is actually referring to the after the combustion. After the combustor, it goes to the turbine. So you are talking about the combustor or combustion temperature. So how does the turbine inlet temperature affect the gas turbine performance? We are talking about combustion temperature lah. It is very straightforward. The higher the temperature, the higher the combustion temperature, the higher the efficiency. Now we are talking about the TH. Okay, remember Carnot cycle, 1 minus TL divided by TH. TL is the ambient, right? TH is the source temperature. So we are talking about TH here. Higher firing temperature definitely will increase the turbine output, and therefore it will increase the efficiency. Okay, however, right, of course we have limitation in terms of the material that is used to construct our gas turbine blade. So that is the only limitation. Unless we can find a new material that can withstand as high temperature as possible, then we might be able to increase the temperature, the combustor temperature as high as possible. Okay. Currently, the typical temperature is around 1,200 degrees Celsius. So this is the kind of limitation that we have. Okay, that's why we require. Engineers have think about method at which how we can push this number as high as possible. They come out with the cooling system. They come out with new material, okay, to withstand the temperature as high as possible. Okay, turbine metal can be protected by cooling air passing through the blade. This is the first stage nozzle and also first stage blade. At the same time, our turbine blade is also coated with ceramic, okay, just to withstand the high temperature. So currently, these are the kind of limitation, right? And then the last factor is, of course, the flow rate lah. I mean, the equation here is fairly straightforward. You have W equals to mass flow rate times the change of Q here. So the higher the mass flow rate, the higher the efficiency, as simple as that. Okay, so that is in terms of the performance. Now let's have a look at in terms of the variation. When we talk about variation here, what can we do? Okay, what can we do to further increase the efficiency of the gas turbine? Okay, gas turbine variation. I mean, the objective of variation, the modification that we can do to our gas turbine is first to increase the efficiency and also to increase the megawatt, to increase the output. So now we are talking about 4 common strategies that power plant is adopting to further increase the efficiency. You can increase the mass flow rate, of course. Okay, you can recover the exhaust heat. This is already done by the combined cycle gas turbine. Okay, but there are other use as well. We will look at that later on. We can also reduce the compressor work. Okay, if you are talking about the back work ratio, remember all the power or work produced by our turbine, 50% of the power is actually being used by the compressor. So if we can reduce the amount of work used by our compressor, definitely we can increase our efficiency. And then we can also increase the firing temperature. So when we talk about variation, currently we are adopting to this method lah. We can use the intercooling system. We can use steam injection, okay, reheating system, evaporative cooling, regeneration, and then you have intercool plus steam injection, and then we have intercool plus reheat plus the steam injection in one system. So let's have a look at this method. We start with the evaporative cooling. This is the simplest one lah. You have seen many people are using the evaporative cooling. Okay, something like spraying the water just to make sure that the ambient is low. Okay, the temperature of the ambient low. This is what we do. Okay, this is what we do in the power plant. At the air intake, you can also spray the water just to make sure that our ambient is relatively at lower temperature. Even if you can reduce the temperature of ambient by 1 degree Celsius, I think that is good enough to increase the efficiency. Okay, cooling of compressor inlet air by evaporative cooler. So they can just put a series of spray at the intake, at the air intake, just to make sure the temperature is cooler. Cooler inlet temperature, it means denser air. Okay, denser air, it means more mass flow rate, and therefore you are having the higher output or higher efficiency. Okay, however, you have to make sure that the water that you spray at the intake is a good quality water. It has to be free from any impurities or free from any mineral matter that could accelerate the corrosion to maybe our compressors, compressor blade, or any other component or parts inside our gas turbine. So currently we can use the fogging method, or you can wet pad. Okay, you can use the evaporative cooling media. You know, when we have a filter in our air filtration system, that can also, I mean, you can just put the water in your filter just to make sure it is wet lah, to reduce the temperature. Or you can use the spray. So this is the the method for evaporative cooler.
So,
Yeah.
is the water used is the same as the feed water?
The water here.
Yes.
Yeah, usually if you're talking about the combined cycle, okay, combined cycle, they are using feed water for the HRSG kan, the heat recovery steam generator. Usually the same feed water they use to spray lah for the gas turbine side. Yes, you have to use a proper treated water for the evaporative cooling. We cannot simply tap in water from the piping system because the water that you have in your piping too they contain mineral, okay, mineral later on that will accelerate the corrosion. Okay, and then we have another method here, recuperative or regeneration. So how does it work? So if you look at this diagram, this is a regenerative or regeneration method. Okay, it means that you are utilizing heat, okay, from the exhaust gas to heat up air that goes into your combustor. Okay, remember when you have combustor for air and fuel for combustion, if we can preheat the air that is used for combustion, you can increase the efficiency of the combustion. So that is the fact that we have to understand lah. The fresh air that is used, okay, to be fed into our combustor together with the fuel, we can preheat them, okay, so that combustion efficiency is increased. So what they do is that they tap the hot exhaust gas that comes out from the turbine, right, and then you channel it to a heat exchanger. Okay, the compressed air which is used to be injected into the combustor will flow through the heat exchanger, pick up the heat from the exhaust gas just now, then enter the combustor. So the temperature here is higher lah than without the heat exchanger. So when you have higher combustion air, it means better combustion efficiency. And when you have better combustion efficiency, actually the amount of fuel that we use can also be optimized. Better combustion, you can reduce the fuel consumption, and at the end of the day, the overall efficiency of a gas turbine increases as well. So we call this method regenerative or regeneration, or some people they call it recuperative method. You preheat the air that goes into your combustion chamber. Okay, then we have intercooling, intercooling cycle or intercool cycle. I think most of the power plant they are adopting this. Okay, before we proceed to the intercool cycle, let's have a look at the basic operations of our compressor. Actually, in our compressor, we can also break it down into low pressure compressor, high pressure HP compressor. Same with the turbine also. We have high pressure turbine, low pressure turbine. Okay, but for simplicity, previously we can just assume the whole lot here as one single turbine. This is just the stages that we have in our compressors and also turbine. Now, if you look at the compressor, remember our compressor, it is made up from blade, which is arranged in many different row. Okay, for every row of blade, no, the pressure increase slightly, and then when you have many rows of blade, so the compression ratio is defined by the final pressure, okay, divided by the inlet pressure. So when you have that row, let's say you are talking about low pressure compressor, high pressure compressor, air that comes into or air that enter the blade, they are, I mean, after the compression though, after the first stage compression, maybe second stage compression, when you have compression, what happened to the pressure? It increase. What happened to the temperature? It increases as well. So for every stages in the compressor's blade though, pressure and temperature increases. So what they do here for intercooling is that they try to lower down back the temperature that goes to each stages of the compressor blade. So this is like cooling lah, cooling of air, okay, for every inlet to the compressor blade. Okay, remember we try to make sure that the ambient is low, just to make sure, just to ensure that the overall efficiency is high. So you're talking about heat exchanger. Okay, let's say in between the low pressure compressor and high pressure uh, compressor, heat exchanger between LP and HP. By doing that, you are reducing the air inlet temperature to every stage of the compressor. Okay, because of that, the amount of work that we use is reduced, and at the same time, you can also increase the power output. Okay, so that is called the intercooling. You are using some medium, okay, maybe water or coolant or seawater, just to cool down the air. Okay, to cool down the compression air that goes into every stage of the blade. So this is, I mean, the main objective of the intercooling system here is just to reduce the amount of compressor work. Okay, and then we have reheating. Okay, just like a boiler, remember we have a reheater. Same thing to the gas turbine. Okay, we have a reheating. Reheating in our gas turbine, you can equate that to afterburner. If you are familiar with the term afterburner that we have for fighter aircraft, okay, they are having a similar concept for the reheating in our gas turbine. Okay, standard gas turbine diagram looks like this. You have combustor. This is where combustion take place. Hot exhaust gas will go to the high pressure turbine. Okay. Usually after the turbine, the hot exhaust gas, we just release it to the ambient. You know that the temperature is still high, maybe around 500 degree Celsius. So in reheating process, you pick up the hot exhaust gas that goes out from the first stage turbine, let's say a high pressure turbine, and then you reburn back the hot exhaust gas, meaning that you have another combustor, you inject the fuel, the hot exhaust gas is already in 500 degrees Celsius, so that it can be easily combusted lah in your second combustor. Then you are producing another hot gas which is used by the low pressure turbine. So this is called reheating process. So okay, it utilizes the hot gas for combustion in the reheater. Okay, so reheater, this is typically another combustion chamber, or we can call that afterburner lah. So by doing that, you are actually improving the efficiency of your gas turbine, maybe from 1% to 3%. So that is the principal operation if you are adopting the reheating process. Okay, the next gas turbine variation method on how we can further improve our performance of a gas turbine is the steam injected cycle. Okay, steam injected steam turbine STIG. This is also very common if you are looking at the name. Okay, we inject the steam to the. There are many places that we can inject the steam. Typically, maybe before the combustor or after the combustor. Steam is injected into the combustor or to the turbine to increase the power output and also to improve the efficiency. Okay, now if you look at the thermodynamics point of view, okay, you are talking about injecting steam into the combustor. We are not injecting water, we are talking about steam. If you inject water to the combustion chamber, what happens? We know that we are going to reduce the temperature. And then by right, common sense will tell us that if you are injecting water into our combustion chamber, of course, we are losing the heat, right? Okay. But for this case, you are actually injecting a steam. You are injecting the steam. In other words, what happened is that uh, the temperature will drop, right? I mean, if let's say if we are injecting the steam based on this diagram just before the combustor. Okay, you have compressed air that flows into the combustor. You inject the steam. What happens? The temperature will drop. Okay, temperature will drop. At the same time, when you have temperature drop, you are actually reducing the temperature here, and generally density will be increased, and therefore you are promoting more air to be injected into the combustion chamber. That's why it says that by doing that, you can actually increase the overall efficiency of the gas turbine. Okay, the reason is that you inject the steam, you are promoting or you are allowing more air to enter your combustor. And of course, when you have more air, the automatic air fuel ratio indicator here, they will allow more fuel, and at the end of the day, you are having better combustion efficiency. Okay, so this is how we have steam injection, STIG lah, steam injected steam turbine, to increase the efficiency. That is one of the advantages. The other advantage is that when you inject water into the combustor or when you inject steam, you are reducing the flame temperature. Okay, if the flame temperature is 1,800, you are producing maximum amount of nitrous oxide NOx. Okay, so if we can reduce the flame temperature to lower than 1,800, for example, so the amount of NOx is actually reduced. Okay, this technology is actually has been proven, and in fact, I think most of the power plant that utilize the gas turbine, they are adopting to this principle, especially for the combined cycle, because uh, you are getting the steam here from the combined cycle, and kalau open cycle, it is kind of possible, but somehow you have to have another system to produce the steam. So you have to invest to that particular system just for the sake of getting the steam. Whereby on the combined cycle power plant, they are already having the steam turbine, or they are already producing the steam, which can also be used to be injected into the combustor. In some power plant, or maybe in a few power plant, they are also injecting the steam after the combustor. Okay, but the principal mechanism remain the same lah. The main objective is to promote more air to come, and the second one is to lower down the temperature of the combustion exhaust gas, so that you are lowering down the NOx emission. Okay, I think the next two method here is actually a combination of one or two of the previous method lah. So let's say, for example, here you have intercooling plus the steam injected cycle. So it means you are adopting the intercooling. Intercooling is you cool down the air that goes that goes through each stage of the compressor. At the same time, you have the steam injected cycle, okay, just to promote more air. So intercooling here, it reduces the compressor work. Steam injected is actually increasing the turbine output, okay, because you promote more air, better combustion, more turbine output. And then you have the last one is intercooling system is there. You have reheat, you have steam injection. So you have three systems combined together, okay, in your combined cycle or in your gas turbine plant. You combine intercooling you together with the reheating, the afterburner, and also the steam injection. Intercooling, you reduce the compressor. Reheat, you are actually increasing the power, increasing the turbine output. Same with the steam injection, we can also increase the turbine output. I think the diagram also more or less similar lah. Intercooling is in the compressor here. Okay, and then you have reheating. So you have two stages to combustor lah in your gas turbine combustor system, and also steam injection. You inject the superheated steam into either in the combustor, before the combustor, or after the combustor. All right, so those are the typical method adopted by most of the power plant operators or gas turbine operators in terms of getting the highest efficiency as high as possible. So we are having a combined cycle efficiency maximum reported so far around 62%, which is generally very, very high as compared to the coal power plant, or as compared to the single open cycle gas turbine plant. Right, that would summarize the topic on gas turbine here. So what are the key important points that you must know? We have open cycle, combined cycle, and cogeneration cycle. Make sure you understand the principal operation for an open cycle, the principal operation for the combined cycle, and also the cogeneration. At least you know how to differentiate between these three types of plant, okay, that utilize the gas turbine. Okay, we know that the gas turbine cycle, it is made from Brayton. Brayton is the theoretical part of the actual cycle for the gas turbine. Make sure you understand what are the processes. You have isentropic compression in the compressor. You have heat addition in the combustor. You have expansion in the turbine. And lastly, you have heat rejection in the heat exchanger for the Brayton cycle. This is just like Rankine cycle that we have for our steam turbine, right? And then we have, you have to identify what are the important component, the major parts that always associated with the repair and maintenance for the operation of the power plant. You have air inlet. When you talk about air inlet here, we're talking about a lot of filtration system, filter that needs to be replaced. Maybe every 6 months, every 1 year, you need to replace that filter. So you have air inlet here. Okay, you know that the air inlet system is very important because we are admitting a huge amount of air into our compressor. Then we have a compressor, you have a combustor for combustion, then you have a turbine. Under the turbine also we have turbine blade. Okay, you understand that turbine blade needs to be cool because it experiences high temperature from the exhaust gas that comes out from our combustor. Okay, and then we have the exhaust system. Okay, exhaust system is different between an open cycle and also a combined cycle. In the combined cycle, the exhaust here will be channeled directly to the heat recovery steam generator, whereby on the open cycle, the exhaust here is channeled directly to the chimney just to be released to the atmosphere. Okay, the performance of the gas turbine, the factor influencing the gas turbine performance, we have air inlet temperature, okay, that goes to your compressor. You have compression ratio, you have turbine inlet temperature, you have exhaust temperature, right? The compressor work, the mass flow rate, and also the pressure loss. Okay, and then we have method or strategy to increase the power output and also efficiency. That is, the easiest way is for us to increase the mass flow rate lah. Okay, increase the mass flow rate of air. You can also recover the exhaust heat Okay, recover means either you use for many purpose lah. Recover for heating up air into your combustion chamber, okay, or having a second combustor after burner, okay. You can also use reduction in compressor work or increase the firing temperature. Okay, and lastly, in terms of gas turbine variation, what else can we do to improve or to increase the overall efficiency of our gas turbine? You can have evaporative cooling. Okay, you spray water uh, to reduce our ambient air. Okay, that is admitted into the compressor. You have reheating. Okay, reheating means second combustor. Regeneration, right? You are actually heating up air that goes into the combustor. Okay, steam injection, STIG here means that you are injecting steam into our combustor, before combustor or after the combustor, just to promote more airflow into our system. Intercooling to cool down the air, okay, at every stage in your compressor, and then the rest is just a combination of 1, 2, or 3 system in one whole system. Intercool plus steam injection, intercool plus reheat, and also plus steam injection. Okay, so that is basically the summary for this topic on the gas turbine. Okay, I think we will stop here, and then for next week, you can prepare. Okay, you can prepare yourself